last but not least, talk before the conference dinner is Ilja, talking about the peculiar source.
All right. I hope you can hear me. Yes. Ending the day with another supermassive black hole binary. I know I'm the only thing that's standing between you and dinner, so let's get this over with quick. So I'm currently a postdoc at CA, and I will present to you this flat spectrum radio quasar, which is a blazar that points at us, J1048. I'm always starting with kind of a multi-messenger picture. What is the ideal source for us or for me is if we have here a black hole or black hole merger that we detected in gamma rays and then multi-wavelengths, in neutrinos maybe, and gravitational waves and cosmic rays, but let's be honest, we won't see cosmic rays from this direction. Neutrinos is a little bit tough, so the only thing I will be talking about are gamma rays, optical light curves, radio waves, and gravitational waves. So coming to the Fermi-Lab light curve of this peculiar source, up until basically beginning of this year or the beginning of 2024, it looked like this. This is the Fermi-Lab gamma ray flux above 168 MeV. It is binned in 5% adaptive binning, meaning every bin that you see here has approximately the same amount of photons in it with a 5% error. And you see here some 4 main flares with a double peak structure, so the so-called subflares. We fitted them with a two-sided exponential function. This is this blue line, what you see here. And what we did is we made a purely mathematical model where we looked at the area of each of these subflares. We computed the centroid of a subflare. So basically, if I would cut out this, the first one, put it on my finger, the centroid would be where I could rotate it and wouldn't fall down. And then we computed the weighted average of both centroids of each main flare and got these green lines, which showed us the center of a subflare, and where it crosses the blue lines, so the outer edges. This is the duration of the flares. This is just mathematically that we computed the duration for each flare the same way. Then it looks like this. If I add now the optical light curve, which is consisting of 20-day binned data from the V band and G band, it looks like this. So in gray, this is the duration of Fermi-Lab, so of a gamma ray light curve, and in red, the duration of the optical light curve. Here, maybe a word, it's done with assassin data and data from a database where hobby astronomers put their data in, but we compared it with assassin data and saw that the hobby astronomers indeed observed this flat spectrum radio quasar, but we did not include ZTF data yet in this process. And the radio light curve looks like this, where we have a single peak structure as compared to this double peaks. And if I print out the flare durations, so here you have the time, here the flare number. We have only the first flare only in gamma rays, but the second and third flare in all of these wavelengths, and you can quite nicely see that we see first the optical flare, then the gamma ray flare, and then the radio flare. For this one, the errors are still, in this plot, still uncertain a little bit because it was done, I think, beginning of 2024, mid-2024. So if I would do the same thing now, so collect all the data, the error would be way smaller, and maybe we could see the same approach there. And if I now look at the flare durations, print out the days here, it's just to show that the durations are approximately the same in each wavelength. and among them one see that the second and third are a little bit shorter than the outer ones. So in order to explain why we see this peculiar light curves, we have evolved, or we came up with the so-called jet precession model. And here I'm jumping into the in-spiral stage of two supermassive black holes at the center of a blazar. So at the stage where the gravitational wave radiation dominates and pushes both together. So here at the center we have the two supermassive black holes. This is the spin of a heavier one. This is the spin of a lighter one. The jets that evolve are launched in the direction of a spin direction. Then we have L, the orbital angular momentum, and J, the total orbital momentum. And here are the angles between them, and we can, because of spin-orbit coupling during this stage, we can describe the motion of each of the jet as precessional around the total angular momentum J. Now, we can assume that this system is stable and that J is conserved on small timescales compared to the in-spiral stage. So small timescales being 10 to 100 years, depending on when we are in the in-spiral stage. But due to gravitational wave radiation, the orbital angular momentum will lose magnitude and direction, and this will drive then the spins towards the total angular momentum. So at a later time t2 during the in-spiral stage, we can have something that looks like this. So the orbital angular momentum moves away from J, the spins move towards J, and then we can describe, for example, for the spin 1, the movement of a spin 1 in the plane of Earth as this kind of donut. And then every time the spin, so the jet, which is here this orange circle, will point at Earth, we will see one flare, and then it will move away and make a circle and point at Earth again. However, because gravitational wave emission is a continuous process, the spins will change, will approach J, over time approach J, so that this donut will shrink in size, so that we will see the next flare faster and faster, so the period decreases. And this will be the case until the time t3 is reached. The Earth leaves this donut, so to say, and we won't see any more signal from this source again. So if we see it as a timeline, and if we are lucky, we will see no signal, then we will see the first signal, then the time between each signal will be smaller and smaller, and then we won't see a signal again. This assumes that the periods have to decrease, and if I print out now the periods between the flares, so this is between the first and second and third and fourth. In gamma rays, we can see, okay, there's maybe a tendency, but the errors are large enough, so it could also be constant. But for example, in radio, we have a small one, but only one data point, and if every multi-wavelength is connected, then we can assume maybe that it's getting smaller, but there's no definitive answer with this plot, unfortunately. But if we plot the main flare area, so basically we have a mathematical structure for each flare. If we integrate over the time under each main flare and normalize here to the fourth flare, we can see that the area under each flare is approximately the same. And what gives this number, it's basically the number of photons that we detect during each flaring episode. And this points us towards the hint that the number of photons is the same, so that this really is a precession of a jet. Maybe another hint that this is really jet precession, what we see If we look at VLA image at 4.8 gigahertz, this is arc second, what you see here. Then this red curve or red arrow is 15 kiloparsec as a projected distance. One sees that it points towards the right. Towards right. If you then take a VLBI image, here's micro arc seconds. Here's a hint. This is approximately 8 parsec is 1 milliarc second. When we see in 2001 that we have something that points down and to the left, and 9 years later we have only something that points down, so that this really is jet precession that we see. We can also compare the SEDs from the subflares. So if I take approximately this subflare, also mathematically determined, here, so the second subflare of the first flare, then the quiescent stage and the first subflare of the second flare, and build the SEDs, so the spectral energy distribution, it will look like this. So this for the left one, this for the quiescent state, and for the right one. So if we just assume Doppler boosting for what we see, it could only move this, what we see, for example, here, move up, down, left, right. But if we compare, I forgot to say it, if we fit it with a log parabola function, then this beta is the curvature parameter, and we see different curvature parameter for the quiescent state than the flaring stage, which also says that what we see is intrinsically different and not something seen at different times. We have also come up with an explanation of a double peak structure, and for that we took the spine sheaf model, where we just assume that the jet consists of a spine comprised of electrons and positrons, and the sheaf has now protons in it. And if we add a target in between us and the binary, the target can be a cloud or a photon field. Then it will come to, when the first sheet points through the target at us, it will come to PP or P gamma interaction, and then gamma rays will come out. So this is why the gamma ray flux goes up. The photon flux goes up as a cascading down of gamma rays, and the in radio flux, which is the synchrotron radiation, will also go up because we have electrons. When the sheet points at us, we only have the synchrotron radiation, so the radio flux goes up, but gamma and photon flux go down. And when the second sheet points at us, we will see again a rise in gamma rays and optical. Yes, and what we did with the jet precession model to the source, we applied it to the first three flares, what we see here. This is a plot from 2022. And we predicted the fourth, and we can predict every flare, and we can predict every consecutive flare, which is basically the assumption that goes behind it. We can analytically model the direction of a spin, and then we can say, okay, after direction of a spin dependent on the time until merger, and then we can say after a period P1, the direction is the same with some errors due to the half opening angle. We can use this to determine the time until merger, and then use the same formula with the time until merger known, and include the period between the second and third flare, and so on, to determine when the next flares should arise. And it agrees with the fourth flare, so this is now a confirmation of our prediction. And what we can do is here you have the time on the x-axis and the mass ratio on the y-axis, and where our confirmation, where our prediction is overlaps with the duration of a fourth flare, we can draw red lines, which is the excluded regions for the mass ratios. We've done the same as an overlap of a prediction, just taking the first period and just taking the second period to get a more tight prediction, and got a mass ratio constraint for this source basically between 0.06 and 0.09. And we can do the same with optical, but because in optical we have 3 instead of 4 flares, the message here is constraint is larger, but it's overlaps. Finally, we can also model the expected gravitational wave emission from the source, but it's the mass of it's basically 1.4 billion sun masses. So its innermost stable orbit will be somewhere way below LISA. LISA will not see it, but we can model that we are now here. The time until merger is, depending on the message, in 25 to 40 years. And we can model how it will evolve with time. And because we use the post-Newtonian approximation for it, here's also a post-Newtonian parameter calculated for this source. Oh yeah, and it has a redshift of 1.15, which goes also in this calculation. Yes, so I'm almost through. Just saying that we applied the jet perception model with a source in optical, gamma rays, and radio data. We constrained the messages. In gamma rays, we predicted that if a jet will point again at us, which is uncertain, then it will happen between 10th of March, nothing happened yet, until the 6th of November next year. And in combination with a spine sheet model, we can explain at least this double peak structure. And we have more data also, like ZTF data, than Weiss infrared light curve and Swift X-ray light curve, which we will also analyze, to have a combined multi-messenger picture. And maybe one last word is also that in the last, let's say, 2.5 weeks, there was a little bit of the source, but it already went down, so it's uncertain if it's the beginning of a new flare or if it's just a random fluctuation. Let's phrase it like this. Yes. Thank you.
Yeah, thanks for this really cool presentation and results. So how, for the spine sheath model, how does this kind of separation result? How do you get this kind of separation in spine and sheath?
Good question. It's not a new model that we came up with, and it certainly has something to do how the jet is launched. So if it's by magnetic force, that protons are heavier than electrons, I imagine, and when this separation comes up, but how exactly, we didn't do a simulation to probe it, but how in detail it comes up, I also don't know.
While people think about other questions, the spine sheet, just to continue that you can probably also derive a neutrino prediction for these outer smaller flares, right?
Not yet, but it's what a master student wanted to do. So we don't have a neutrino flux from the source, but one can, because we have data for 15 years, one can say in 15 years how many one could expect and then make upper limits. Yes.
Thanks. That was it's a really exciting source. Well done for finding that. Got a few questions. Maybe you answer some of these and I missed it. So do you know much about the actual galaxy itself from, like, I don't know, optical observations or something else?
It's a blazer, so we don't know anything about.
There's no detection.
No, because we no.
Okay. Did you say what Z it's at? Sorry, I missed that.
Sorry?
What Z? What redshift?
1.15.
Okay. And you've got Swift light curve that's coming. Is that the idea?
Yes, unfortunately, here we have only some data here, some here, and here. So nothing for the quiescent stage because it's the X-ray flux was, I think, low, so that no observations were issued.
Okay, and you've got more data coming, or?
Yes.
Okay,
Yes.
cool. And you're going to cover hopefully the part where it shows peak as well, or
Yeah, for this flare at least.
have you thought about
This
looking at
this is yes, we have two other wavelengths. We are right now collecting all the data, analyzing it, and preparing a nice, hopefully small paper.
Cool. Looking forward to that. Have you thought about looking at with XMM as well?
Sorry?
Have you thought about observing it with XMM?
No.
Might be interesting.
One last question. Then let's thank Ilja again and all the speakers.